I'm Emily Riehl. I'm a mathematician at Harvard, and today I want to tell you about my favorite algorithm, which solves something called the stable marriage problem, or sometimes the stable matching problem. You might ask firstly what an algorithm has to do with mathematics, and that's a fair question. This is a part of mathematics that's called game theory that sometimes falls under the purview of computer science or economics or something like that. But the reason I really like this algorithm is it's relatively easy to prove that it has a number of really remarkable properties, and so we'll get to that later. But first, let me describe the problem. So suppose there's a remote village, maybe on an island in the middle of the Pacific, with one tribe living on it, and say there are 10 marriageable men and 10 women, so 10 single men, 10 single women of marriageable age. The tribal elders want to pair everybody up, and they want to do so in a stable fashion. So what stable means, or maybe what is not stable, would be a situation where there's a danger that some unmarried couple will run off and elope. So say this man is paired with this woman, and this man is paired with this woman. But this man in this couple prefers the woman in this couple to his current partner, and simultaneously the woman in this couple prefers the man in this couple to her current partner. If that's the case, there's the danger that these two will get in cahoots and run off together, and so that's the situation we want to avoid. So, I guess one way to say it is stability is if every woman that a given man prefers is matched with somebody that she likes better to him. Even though I didn't say that symmetrically, it turns out that's a symmetric condition. So if it's stable for the men, it's stable for the women. I might apologize right now. This is a really heteronormative algorithm, solving a heteronormative problem. It turns out that if same-sex coupling were allowed, the problem becomes much more difficult. I'll have something to say about that a bit later. But anyway, allow me to continue. So I guess the goal in this situation, the tribal elders want to arrange marriages so that this does not occur, so that all the couplings are stable. So find stable marriages for everyone. Okay, so we've defined the problem, which is to pair up the 10 men and the 10 women in heterosexual marriages so that there's no couples who will elope, leave their current partner because they simultaneously prefer each other. Now that I've said the problem, I should point out that it's not obvious. Well, firstly, that stable marriages exist. That it's even necessarily possible to pair everybody up so that the stability condition is satisfied. It's also not obvious, given that stable marriages exist, that, I guess, if so, it's still not obvious that they can be found. So suppose now this, village on this remote island grew in population, so now there's 10,000 men and 10,000 women of marriageable age. In that situation, maybe there is a stable matching, but there's so many possibilities that it might not be practical to find it. So what's remarkable is that this algorithm is going to have both these properties. It is going to provably find a stable marriage in any situation, stable matching for all the couples, and secondly, it does so really rather efficiently. All right, so let's describe how this works. So the algorithm was first studied in a paper in 1962 by David Gale and Lloyd Shapley. So here's how it goes. So before the algorithm begin, so the men rank the women. That is, each man in the village ranks all the women in the village from 1 to 10. So comes up with his preferences. I prefer to marry her, otherwise her, if not, then her, so on and so forth. And similarly, the women rank all the men from 1 to 10. So everybody comes up with their list of preferences, and so now the algorithm begins. So on the first day, maybe we'll say in the morning, each man proposes to his first choice. So each man, says to his top woman, will you become engaged with me? And then in the afternoon, so some women will be in the happy situation that they've received multiple proposals, and in that case, so each woman rejects all but her top suitor. All but her top suitor. And to the top suitor, she doesn't say yes for sure, but she says maybe. To whom she says maybe. So if you don't receive any proposals on the first day, you don't do anything. If you do, you say no to all but your best option, and then you say tentatively yes to that person. This algorithm belongs to a class of algorithms that's called sort of deferred acceptance, and this is sort of the deferral. So what happens on day 2? Well, so at the end of day 1, the night of day 1, some people are tentatively engaged. So men who made a proposal that was successful are engaged. If they were rejected, then those men are called unengaged. And in the morning of day 2, the unengaged men propose to their next top choice. So if they were rejected by girl number 1, then the men will propose to their second best girl. Then in the afternoon of day 2, the women have a chance to trade up. So maybe I'll just say that. Women may trade up. So a woman who's holding a proposal from day 1, who said maybe to some guy on day 1, might receive a proposal she likes better on day 2, in which case she'll reject the person who proposed to her on day 1 and become tentatively engaged with the person who proposed to her on day 2. And then this algorithm repeats like this, so 3, 4, 5, etc. We repeat until everyone is engaged. So if at any point, well, so what this means, of course, is, after the end of day 2, there will be some people perhaps who are unengaged. It's possible that a man might be engaged after day 1, but then rejected on day 2, so he's back to being unengaged. All men in that position will propose to their next best choice. The women can trade up again. And if at any point there's some evening where every person in the village is engaged to somebody, then that's the match. The algorithm stops. Okay. So you might have some questions about, does this actually end? Does this work? But before we get to that, maybe let's do an example. Okay. Right. So before the algorithm begins, the men need to rank all the women need to rank all the men. So if I had 10 men and 10 women, this might take a bit too long. So let's suppose we're in a village with 4 women, say Amy, Beth, Kathy, and Dee, and 4 men, Jim, Ken, Leo, and Max. So for the algorithm to begin, each woman has to rank the men 1 through 4, and simultaneously each man will rank the women. So say Amy's prefers Leo to Jim, then Ken, and Max, while Beth likes Jim best, then Max, then Leo, then Ken. Kathy likes Ken, Max, Leo, Jim. Dee likes Max, Ken, Jim, and Leo. So these are the preferences from first to last for the women. And similarly, the men rank all the women. Say Jim likes Amy, then Dee, then Kathy, then Beth. Ken likes Amy, Beth, Kathy, Dee. Leo likes Beth, Dee, Kathy, then Amy. And Max likes Kathy, Amy, Beth, and Dee, in that order. Okay. So supposing this were the preferences in some village, let's see what happens. So on day 1, each man is going to propose to his top choice. So Jim proposes to Amy, Ken also proposes to Amy, Leo proposes to Beth, and Max proposes to Kathy. So in other words, Amy receives 2 proposals from Jim and Ken, Beth receives 1 from Leo, and Kathy receives 1 from Max. So in this situation, Amy holds 2 proposals, so she rejects the one she prefers least. So maybe a good summary of what happens on day 1 is that Amy rejects Ken. So at the end of day 1, Ken is unengaged. So Ken, then on day 2, he was rejected by Amy on day 1. On day 2, Ken proposes to Beth. So Beth now has a second proposal from Ken. So she received a proposal from Leo on day 1, and that she still prefers. So in day 2, Beth then also rejects Ken. So at the end of day 2, Ken is still unengaged, having been rejected by Beth on the second day. So Ken then proposes to his third choice, which is Kathy. So Kathy now receives another proposal from Ken. Now Kathy's tentatively engaged to Max, but she actually prefers Ken. So now Kathy is going to reject Max. Kathy rejects Max. So on day 4, Ken is now finally tentatively engaged with somebody, but Max is back on the market. So Max now proposes to Amy. Amy is currently holding a proposal from Jim, which she prefers to Max, so Amy is going to reject Max. Amy rejects Max. Okay, so Max is still unengaged on day 5, at which point he proposes to Beth, who's the next on his list. And Beth indeed prefers Max to Leo, who she was tentatively engaged with, so she'll now reject Leo. So Beth rejects Leo. Leo, now being rejected, is back on the market, and in day 6, Leo proposes to the next person on his list, which is D. D doesn't like Leo very much at all, but she doesn't hold any other proposals, so she tentatively accepts Leo. And now you can see that everybody is matched up. So on day 6, it's a match. The algorithm terminates, and we have the following couples: Amy with Jim, Beth with Max, Kathy with Ken, and D with Leo. Okay. Right. So again, as a mathematician, what really excites me about this algorithm is that we can prove a number of properties about it. So let's go through some theorems. So the first theorem, maybe we should call theorem 0, is that this algorithm always produces some sort of marriage. So this algorithm terminates. Meaning, no matter how many people, how many men, how many women, no matter what the preference lists are, if you run this procedure, it'll always stop in a finite amount of time and yield some sort of matching, some sort of marriages. This is a really cool result, and I guess I want to leave it as an exercise, give you an opportunity to think about how to prove it. Maybe I should give a hint, though. So what's characteristic of the day on which the algorithm terminates, that's not characteristic of any days previous to it, is that everybody has received a proposal. So you'll note in our example, this algorithm stopped when D received her first proposal. And you might want to, there's a little more to think about here, but that's going to indicate when the algorithm stops. So, okay, so the algorithm stops, that's good. But the problem that we pose is we want to find not just any marriages, we want to find stable marriages. So where no man prefers some girl who also prefers him. And I guess that's theorem 2, is that the marriages produced by this algorithm are stable. And this result's actually fairly easy to see. So it's the reason that the marriages are stable is, let's think about it from the man's perspective. So each man is matched with some woman, and all the other women, all the women that he prefers to his life partner, rejected him because they got an offer from somebody better. So by definition, it's stable because all the women that any man prefers are with somebody they like better. So great. So we've solved our problem. Remember I said at the beginning that it wasn't clear that stable marriages would exist in any configuration, and we've just proven that they do because we have an algorithm that always finds stable marriages and runs rather efficiently. In fact, you can try this on your friends. It's easy to do yourself. Okay. But here's what's even more remarkable about this algorithm to me, is that not only does it find some stable marriage configuration for everybody in the village, but all men in the village are simultaneously paired with their best possible mate. Simultaneously, yes, we matched to their best possible mate. And what I mean by this is that, so we've just shown that there exists at least one stable marriage configuration. So there's one way to match everybody up in the village so that all the marriages are stable. But there might be more than one. Indeed, in some examples, there can be quite several. But of all the stable marriages, this algorithm optimizes, I guess, the men's happiness or something simultaneously. So there is no other stable marriage configuration in which any of the men do any better than they do in this one, which, if you think about it, is really a remarkable fact. Okay, so these three results are due to Gill and Shapley, who published the first analysis of this algorithm. And it makes it seem like it's a fantastic algorithm. In fact, it is really a fantastic algorithm. It's very rare that a problem in game theory will have a solution with all these remarkable properties. But there's one more result due to John Conway, I think in the 70s. So we have this wonderful solution that optimizes the preferences of all the men in the village. It runs very efficiently, finds stable marriages. The only issue is that while all the men are simultaneously paired with their best possible mate, all the women are simultaneously matched to their worst possible mate. So again, among all the different stable marriages, each of the women is with the worst possible guy. So from the girl's perspective, this is really, really bad. And actually, to illustrate, if we go back to our example, you could imagine, I mean, this is kind of a patriarchal algorithm. I guess the men are proposing and the women just sort of passively receive proposals and try and do the best they can under those circumstances. We might ask, what would have happened if the women were the proposers, if the women sort of had the opportunity to act first? Well, and let's see what happens in this case. So on the first day, Amy would propose to Leo, her top choice. Beth would propose to Jim, her top choice. Kathy would propose to Ken. Dee would propose to Max, which means Max receives a proposal from Dee. Ken receives a proposal from Kathy. Jim receives a proposal from Beth. And Leo receives a proposal from Amy. So in this case, you can see the men aren't maybe the most thrilled about these proposals, but each man receives only one. So the algorithm terminates. Each man will accept the women. And if the women had proposed and not the men, what would happen is every girl gets her top choice guy, and the guys just kind of have to deal. So you can see this asymmetry. The men in this stable configuration all do worse than they did in the sort of male optimal algorithm, and simultaneously the women all do better, which is exactly what was guaranteed by theorems 2 and 3. Okay. Right. So the last thing I want to say about this algorithm, and maybe the other reason that it's my favorite, is that there's a real-world application, and it's a really important application. This is called the National Resident Matching Program. So this is one of those perhaps rare instances where the mathematics really matters and affects people's lives. So every spring, across the country, tens, maybe hundreds of thousands of medical students graduate, and the next step in their training to become doctors is that they enter a residency. So it used to be that in the 1940s maybe, that the application process was very chaotic. The residents would try and, or the hospitals would try and gamble for the best residents by, forcing them to accept offers earlier and earlier, sometimes as early as their second year of the 4 years of medical training. So this was a bad state of affairs, and instead, the medical boards got together and instituted an algorithm, and in fact the algorithm that they adopt is precisely this one, the algorithm that solves the stable marriage problem. So what happens is that the medical residents will or the med students will apply to residencies, they'll interview at some hospitals, then they'll submit a rank order preference list exactly as is necessary for the algorithm. Simultaneously, the hospitals will rank all their applicants, and then the computer runs this algorithm, and one day in March, every medical student receives an envelope that tells them what their matching is. So this is a real-world application of this algorithm. Okay, so in light of some of the theorems we've just proven, you might ask, well, who gets to be the proposers? We saw that in this algorithm where the men propose, their outcomes are simultaneously optimized, where the women who receive the proposers' algorithms are not optimized. And indeed, for the first, I guess, 40 years that this algorithm was run, that part of the theory wasn't very well understood, and the hospitals acted as the proposers. So the hospitals got the best possible slate of medical residents, and the students sort of did as poorly as they could in any stable configuration. Fortunately, in the mid-1990s, Alan Roth, a mathematician, economist, game theorist, got involved and sorted things out, so now that the medical residents get to act as the proposers. So it's a much better state of affairs. So you can tell your friends in medical school that they can have some sort of confidence in this sort of mysterious behind-the-scenes procedure that determines the rest of their lives. Okay, right. That said, when you do enter the real world, there are some additional complications. So one complication that faces a lot of med students these days is they're not acting as an autonomous body. You know, maybe they're part of a couple. They're, you know, two real-life married medical students who want to match to residency programs in the same city, say. And so the algorithm that's used by the National Resident Matching Program allows what's called a couples matching, where people's preferences can be tied together. You know, I only prefer this program if my partner can get into this program. Unfortunately, if you tweak sort of anything in this theoretical framework, it becomes a much, much more difficult problem, and indeed there might not be a stable solution. So in particular, it's been proven that this couples matching, where you're allowed to, you know, throw your hat in the ring with a partner, makes the problem what's called NP complete, which means if you had an efficient solution to this problem, you could solve a whole litany of other, you know, extremely hard problems. You could figure out how FedEx should route packages most efficiently across the United States, anything like that. So fortunately for couples, this doesn't necessarily work quite as well as the singles algorithm. Okay, so the last thing I want to say is I want to leave you with an exercise. So of course this whole discussion was very heteronormative. It's, you know, it's not just because people were kind of sexist in the 1960s, but it turns out that, say, our remote village now was occupied only by women and they preferred to match with each other. That problem might not always have a stable solution. So in the PC era of the 60s, this was called the stable roommates problem. So the exercise, if you'd like to think about this some more, is that you should show or prove by example that the stable roommates problem may have no solution. Stable roommates problem might have no solution. So what I mean by this is, you know, make up a collection of individuals and let them rank each other in terms of who they'd like to pair up with for a rooming assignment, and find an example so that no stable configuration can be found. So thanks very much.